Hello, I'm hoping this is the most important math video that you've ever looked at. I am trying to see if I can find a better way of teaching math. And what I'm asking of you is to challenge what I'm teaching you in the same thing, in the same way that I'm challenging the way math has been taught already. So let's get started. Each of us have a limited knowledge of math that we understand, independent of what we're taught. To some extent, we are confident of that which we know. However, we have given up that independence by accepting some other person's viewpoint without doing the validation to prove that their viewpoint makes sense. These people may have national reverence for their knowledge or viewpoint. We then become part of the lemming mob marching to the brink of ignorance. We are going to show you how to regain that intellectual independence and confidence and to apply that knowledge to the problems of the world. So we begin with this optical illusion. At first glance, this looks like a three-pronged fork called a trident. But if we look at it closely and try to manufacture or construct this, we see that we can't do it. It's an optical illusion. So our brain interprets these lines and circles in one way, but in reality, it's different than what we interpret. And this is what we're dealing with in the learning process. Now, below this line, or below this trident, is a point, a line, and some parallel lines. Oh, you can't see them. Oh, because a point has no dimension, a line has no width, and parallel lines are made up of lines. But we use a dot or a thick line to indicate these. And so we're enhancing our imagination with those optical illusions. It was difficult for me to develop this paper because it violates all that I was taught about math. I did not realize that my US patent, filed in 1979 and 7 years later was approved, violated the geometric definition of lines. My article in the 1969 issue of the Harvard Business Review could be interpreted as a warning of the dangers of artificial intelligence. Fortunately, math has a way of being checked and having multiple ways of looking at something. The hardest part was proving to myself the hypothesis that I was making that I'm going to be presenting to you. To prove that this view of mathematics to others is better than the way we are taught. It is a challenge. So let's take a look at negative numbers. About 1,300 years ago, Brahmagupta came up with a way of presenting negative numbers with lines. Okay, and I took that information and turned the lines into vectors. And from what I understand, one of my students, this information that was available 1,300 years ago is starting to be used. Okay, so if we look at a positive number or number one, it's a line that moves to the right. A negative one is a red line with a number moving to the left. Now, I could just use right and left, but the color makes it stand out a little bit more. So if we're adding a 3 to 2, we have those three positive lines added to two positive lines, we'll get 5. If we minus 2 to minus 3 is being added, we get a negative 5. It's most obvious when we use these manipulatives. You'll notice in each case we're starting at a 0. That's what that point represents. Okay, so now we take a plus 3 and add a negative 2 to it. Okay, and what we see is we have a plus 1 left over. On the other hand, if we take a plus 2 and add a negative 3 to it, we have a negative left over. So it becomes obvious what happens when we add numbers of different sizes. The rules stand out. And a little bit better than we use the tiddlywink approach of doing this. For subtraction, what we find is for negative number, when we take a negative of a number, it becomes a positive number, it becomes a negative number. When we take a negative number, it becomes a positive number. We're just basically flipping our lines. So if we want to add minus 2 to minus 3, we flip that minus 2 becomes a plus 2, and we have 3 plus 2 is equal to 5. If we want to subtract a minus 2 from minus 3, we flip that minus 2 again, it becomes a plus 2, and we get a minus 1 in the answer. So this particular way of presenting things makes it easier for our mind to grasp what's happening. Now, when we subtract negative numbers, we're going to make up, we already made up the rule that the numbers would be flipped. So in this case here, we take a negative 3 and add to it a plus 3, we get back to our start, or 0. So let's take a look at what this concept helps us. We're now defining a negative number such that when it's added to its positive complement, we get 0. And if we subtract 3, we get minus 3 is 0 minus 3. So now we're beginning to see how the notation for a negative number is defined. Okay, and there are other things you can look at on your own. Here I'm now taking a 0 plus a 0 is a 0. But now I'm using the commutative and associative properties. I bring the negative numbers together, the positive numbers together, which is changing the order of them, and then grouping them. If I now take this positive group and move it over to the other side, I'm doing a subtraction. And we already see that 0 minus a number is a negative number. So minus 3 plus minus 2 is equal to minus 5. I feel so much better. I hope you do too. Another approach to this is pretend we don't know about 0 and negative numbers and just call them letters B, A, and Z. Well, we know we create our numbers by adding 1 to the previous number. So 3 is equal to 2 plus 1. 2 is equal to 1 plus 1. Okay, so there's our counting process that we have in terms of positive numbers. Well, the number before 1 is 0 or Z, so we just add 1 to Z. Well, since 2 plus 1 is 1, we can replace that by Z plus 1. And then we can take and we can commute them, so they're in different orders. And now we regroup them, and 2 plus 1 is 3. We add Z to it, so we see that Z added to 3 gives us 3. Not because 0 is nothing, but because 0 precedes the number 1, the starting point, as we saw with negative numbers. Now let's take a look at something else. B is equal, but plus 1 is equal to A. And A plus 1 is equal to Z, which we now know is 0. So we have, if we add 1 to the B, B plus 2 is equal to A plus 1, and we know that A plus 1 is 0. Now we move the 1 to the other side, the 2 to the other side, and we get A is equal to 0 minus 1, which we call negative 1. The same thing with B. We now put minus 1 back in here. We get minus 1 plus 1 is equal to 0. Minus 2 plus 2 is equal to 0. Okay, that's what we learned with our pictures. Now we're learning it algebraically. Now, we know that 2 plus 0 is equal to 2. If we subtract 2, we get 0 is equal to 2 minus number. Subtracting a number from itself gives us 0. But instead of using U, if we put 0 in the place of 2, we get 0 is equal to 0 minus 0. Well, we know from our definition that this is a negative 0. So 0 has a sign. This tells us that negative 0 and 0 are in the same place. So this is refuting a number of things I've seen recently, including some videos on television. Okay, now let's look at areas and perimeters. The books will tell you that areas don't have signs, and neither do perimeters. But let's look at this another way. This black rectangle inside of this, to get the area of this around here, would be treated as a whole. And so this area, if we considered a negative area added to the big green area, would give us this area. But if we put this black triangle outside, a little bit hard now to think of it out here because we think of it as a whole, but think of it just as a black triangle. We add these two to get to the total area. So now let's look at perimeters. If we go around in this direction and recognize that this is a positive direction, this is a negative direction, what we'll find is this little triangle, because you can't see it because you can't see the lines that make it up, would be subtracted from this big rectangle or big polygon, and we would get a positive area. But if we go around in the opposite direction, this now becomes positive and this becomes negative. So now adding this positive triangle to the negative triangle, we get a negative area. So we've now shown that signs for areas and perimeters does help us understand things a little bit better, or at least see them differently. Do lines have sides? Well, if this line is going in this direction, then D is on the left side, E is on the right side. If it's going in this direction, D is on the right side and E is on the left side. And we see in one case, the distance D is negative. In another case, the distance D is positive. So we've shown that a distance can be positive or negative depending on how we look at it. And when we think of vectors, this doesn't bother because the negative number is a sign. Now, with the counting numbers, I would like to have shown this with the vectors and so on, but I think at this point you can see it without the geometric manipulatives. So 3 times 2 means we have 3 2s, which adds up to 6. 3 minus 2s would be minus 2 plus minus 2, which we know from our negative numbers adds up to minus 6. Well, we're counting the negative 2s. Okay, so why? Maybe because we sprayed some mist on our numbers and they became negative. But we're counting them. For negative numbers, when we subtract a number, we flip and add. So if I have 3 times minus 2, I would add these 2's up, get 6, flip them, and I get a minus 6. Okay, so if we're adding or counting 2's with a negative 3, we add them up and we flip. It took me a while to come up with this concept so I could see it better. And now, what's really interesting, if we're adding a negative number, multiplying, counting negative 2's with a negative number, there's our negative 2's, which we add up, which give us a negative 6. And then a negative number flips it, we get a positive 2. Such an easy proof. I was impressed with myself. Okay, you may not be, but let's continue on. Okay, so now we go take a little step into imaginary numbers. Imaginary numbers, starting with Euler's formula, can be written from an exponential into a sum, a real part and imaginary part. And if we use an imaginary space in which to plot these in, the real part is projected on the real axis, and the complex part is projected on this axis. And what we're discovering is we're using angles in here, which now gives us a rotational concept when we're using negative numbers. So by using this as a vector, we see negative numbers in a different fashion, and we see that they have a rotational property. They also have an orthogonal property, which is quite not as obvious. So these different ways of looking at it have introduced complex numbers and rotation. I like this. And if we look at this, we find that this gives us an introduction to the quaternions. Now let's get back to multiplication and counting numbers. Multiplication is associative and commutative, as we're told in our books. Matrix multiplication is not commutative. It sends up some flags. But if multiplication is associative and distributive, then it holds for real numbers and matrices. Okay, so let's take a look at these properties. 5 times 1 is 5 ones. We add them up, and that's 5. Okay, so we have 5 times 3. We can replace that 3 with 3 ones. But the distributive property allows us to multiply the 5 times each one of those ones. And we know that 5 times 1 is equal to 5. There are 3 5's there. So we've now shown that 5 times 3 is 3 times 5 using the distributive property. This means we don't depend upon the commutative property to to make it easier for arithmetic. We've derived it, so it's not the fundamental property anymore. So now we've shown, at least in my opinion, that negative numbers are counting numbers. Okay, now let's take a look at multiplication again. I'm going to define 3 times 2 as 0 plus 2 plus 2 plus 2 instead of just 2 plus 2 plus 2. Okay, now if I had used 3 signs, then this would have come out a different number. I made a mistake on this slide. But I wanted to show basically as we went down, we were counting down 1 less. Okay, but let's not worry, or I'm not going to worry about it. Okay, so what we notice, we're dropping a plus 2 each time we go down. And we find, if we look at this again, from a skip count viewpoint or geometric viewpoint, we're starting with 0, 1 skip count, 2 skip counts, 3 skip counts. But if we look at it from the conventional way, we're starting from 2, just as we started from the 0, and we're just doing 2 skip counts. Get the same result, but it gives us a different perspective on how we're looking at it. And over here, we'll notice plus 2, but we're not dropping a plus 2, we're dropping a 2. So we don't need the commutative property to tell us that 2 zeros are 0 and then turn them around. It falls out from a new definition of multiplication. Okay, so let's look at factorials. These both are negative factorials, negative 2 factorial, negative 3 factorial. And based upon some work I've done, this comes out to minus 2. But if I go to calculator on the computer and put in minus 2 factorial divided by minus 3 factorial, it tells me it can't do it. But if I take and put, instead of minus 2 and minus 3, a little bit away from that, it gives me minus 2.01, pretty close to my minus 2. If I make it even closer to minus 2 and minus 3, I get an answer that's even closer to minus 2. If I come in from the other direction, I get minus 1.99, which is very close to 2. And if I put more 9s in there, it gets even closer. But what we notice is it doesn't quite come out to 8 9s as it did before, but it comes out still closer. But we've seen some things happen in the calculation. So computer programs do not necessarily perform correct calculations. We had to use differential calculus in order to prove that the conclusion I draw seemed to be reasonable. So let's summarize what we've done so far. Okay, we've redefined the definition of multiplication. We've redefined the concept of 0 as no longer being nothing and being the integer before 1 and having a sign. He showed the importance of the distributive property in multiplication. So we didn't need to use the commutative property anymore, or directly. We still used it indirectly. Negative signs, we now are interpreting as a direction for a vector. More importantly, the whole thing started with the definition of a counting number, which we redefined and expanded it from positive integers to negative integers. We showed that lines had sides and direction, and we showed that distances had signs, and that areas and perimeters had signs and direction. So we've looked at things in a very different direction. Now, what you have to do is look at this again and have a discussion with yourself to see whether you agree with me or agree with what you were taught. Okay, and then have a discussion with a friend who sees things the same way I see them, and see if you can convince each other to take one side or another. You do this, you will understand math and number structure far better than you ever did before. Thank you very much for listening to what I had to say. Actually, I'd like to say in person, thank you very much.